society, for the opportunity to make me work hard and think back. So what I want to spend the next 35 minutes on is my personal trajectory, which has obviously been influenced by what's happening around. So I joined Sydney University on the faculty there in 1966. And I was lucky because Sydney University had had a computer for 11 years by then. If you were involved with computing, the top left-hand corner shows the professor working on the computer. That's what that meant in those days. You took a screwdriver and you moved things around. By the time I got there in 1966, the computer was already hidden behind walls. You couldn't get near it. And you'll notice, by the way, that already people there had long hair when they worked on computers. Our means of communication were punch cards. You had to learn what all the holes meant because there was nothing written there. But amazingly enough, we did. So when I said, as a new faculty member, I wanted to study design, the professor of engineering told me that design is a mystery that fundamentally cannot be understood. Very prescient gentleman. The professor of architecture said, if you do get to understand design, you will destroy it. I thought, But anyway, I continued. At that time in the 60s, there were lots and lots of ideas about computers, but very few computers. Christopher Alexander had done a PhD in 1964 at Harvard and published it, called Notes on the Synthesis of Form. Herb Simon had been talking about information processing models of reasoning and published his Sciences of the Artificial in 1969, where he chose design as his vehicle. And then Herb Simon and Alan Newell published Human Problem Solving, which was based on artificial intelligence. These were this was the environment. It became clear that what could we do were things like get computers to do things we already knew how to do. And most people were building models based on mathematics or physics. But this, in design terms, just didn't look interesting because we didn't have such models. They were mainly engineering science models. So I got interested in things that had no mathematical models. And we started to build models of city planning codes, funded by IBM, by the way. And then economic models, which we combined with city planning models. In fact, my first PhD student was in this area, and he was also the first student to leave me without getting a degree. He started up a company that took all these ideas and actually made money off them. We moved very quickly into graphics. Graphics then was line printer graphics, and then only later did we get line graphics. These are all examples of as either one or two bent lines just translated and rotated that produced emergent properties, which was really an interesting topic in the 60s and continues to be today. There was a surprising amount of interest in practice. So a few years later, we started these courses, evening courses, that turned into graduate degrees over the years. Simulation had a problem, which was that it told you about things but didn't generate anything, didn't produce anything. Optimization, however, looked very much like the solution to this problem of how do you get to answers rather than telling us more about answers we already had. And we did really quite interesting work there. there is an idea called Pareto optimal design, which is the best designs you can generate. And we were able to show that you can do better than Pareto optimal if you're a designer, because designers don't work within a fixed space. And this is a recurring idea in studying design, that if the space of possible designs can be changed, particularly based on what you've been doing, you can end up in better places. And we were able to show that this was possible. This sort of work turned out to be interesting in industry, and we got involved in lots and lots of projects. I started a company to do this. I wish I could say it made a lot of money for me. What it produced was an enormous number of headaches, but there's a special thrill in being involved with real projects, and particularly very large-scale projects. In the sort of early 70s onwards, artificial intelligence became the major intellectual driver in lots of areas, and also in design. In those days, it was called knowledge-based design. The question was, how could you represent designs symbolically, not graphically, and not mathematically? So this was a hot topic, followed by reasoning. And reasoning then meant things like rules, and we had very large-scale rule-based systems, which were then called expert systems. Logic, where you could trace through deduction the outflow of a set of ideas, and then planning. And these became models of design. We soon discovered that without learning, you just produce the same result every time. So we got very interested in learning, which then was called machine learning, and produced design rules, ways in which you could capture, given examples, some abstraction of what might have been used to drive it. And this was pretty exciting stuff, because now you could produce a set of designs manually, get the machine to extract these rules, and then reproduce those designs and others. And then we were able to go further and find patterns of rules. And out of that, we also got involved with design grammars, which are a particular class of patterns. And then neural networks hit the scene. And this was now the late sort of mid-80s. And like everybody else, we got involved. What we discovered was that neural networks were really good at capturing designs, but not very good at producing designs that were different to the set from which they were captured. The sort of thing you could do was, here's an example of a retaining wall expert system. A retaining wall is a piece of structural engineering that holds soil or water back. And this wasn't a parametric model. This was a model that contained knowledge of expert designers. And that's what was used to produce these designs from the problem definition that varied every time. And of course, we produced a book, Knowledge-Based Design Systems. 4 of my former PhD students and I wrote this really fine textbook. I had a look at it for this talk, and it's still very good. A little out of date, but very good. And then I started these conference series to try and bring together a community that was working on this. Out of all that came an interest in creativity, and Mary Lou Meyer and I organized this conference in December '89 on a small tropical island in the Great Barrier Reef of Australia. I can recommend the place even if there's no conference, but if there is a conference, it's even better. And we held that conference regularly for many years, and in fact, last year we held the 30th anniversary conference. The place is still as good as it was. We produce books on various topics related to design creativity, and I thought I would just pull out one example of the sort of work we were doing that was a little different to the work of many others. I had this idea that genetic engineering, which is the notion that there's something in the genome of an organism that is connected to its behavior. And this was found in the health area, where initially they were able to locate unique genes that cause certain diseases, and in particular, patterns or structures of genes that, when they occurred together, produced unfortunate consequences. So I took this idea and inverted it and said, what if we produce a set of designs represented genetically, and take all the good designs and see if there's something in their genomes, in their genetic makeup, that they share that isn't in the bad designs. And out of that, we produced genetically engineered genetic algorithms, which were shown to outperform genetic algorithms fairly dramatically. And then we applied it. So you give it some examples, it genetically engineers genes from those examples, and now you can produce designs that have never existed before. And you can do all sorts of things, like on the left are genetically engineered Mondrian paintings. On the right are genetically engineered Frank Lloyd Wright windows. And then you can get Mondrian and Frank Lloyd Wright to mate, or I mean, not literally, just their genes. And now you get Flondrians that have never existed before. So this opens up the possibility, and this is what we're always interested in, of how the design space within which you're working can be changed. It became clear that you needed something more foundational than constantly coming up with individual ideas, which you could then turn into algorithms. And this was something that was sort of a meme that was floating around, that you needed something more. And this resulted in the function behavior structure ontology, which has become a sort of theoretical foundation for much of what follows. Later on, we extended this to situated cognition, to what became the situated FBS, the idea that a person sits in the world, and inside the head of that person is what you want the world to be, because that's what designers do, they change the world. This is what's behind it. There will be a test a little later on this. But what you could do from this is build agents that knew about what was going on around them and behaved autonomously. And you could turn that into design, like here's components, and they would self-organize. Or here's another example where we want computer programs to talk about the same design, but they don't know how to talk to each other. So they learn how to talk to each other. And then you can take these ideas of situated agents and use it to study how human teams behave. We know that when people form a team, over time they get more efficient. That is, they're able to produce results faster, but they also end up producing fewer different kinds of designs, and we can model that computationally. And hopefully this is not stuck. Whoops. And it was. So there's one slide it doesn't like. Okay, so from there we moved on to, remember, this is a Microsoft product. So one has to assume, let's assume it stops here for the moment. You could build models to test ideas like novelty. Something should only be novel once, or it should have the potential not to be novel when the world changes. And this is a series of studies with Maria Perisic that shows how novelty changes as you continue to design. Well, all of that looked good, but what happens when you get humans, because designers are humans? And so we got interested in modeling or understanding what happens inside people's minds, and that's design cognition. And protocol analysis is a method of listening to people and extracting what is in their minds from just listening and watching them. And you can get amazing results from this. And this is sort of just indicative. If you take, say, mechanical engineers in their first year, before they specialize, before they pick a major, and you give them a design task and measure their design cognition, and then a couple of years later, you measure their design cognition again after they've specialized, you can measure the differences in the way their mind works. And it doesn't matter what this particular slide shows, that's profoundly important if you're an educator, because if there were no differences, we would have been wasting our time. This is a really nice example. Teams. There's three groups of teams here. The pink are industrial designers, the dark green are mechanical engineers, and the light green in between. And the vertical axis measures where they spend their time in relation to the problem or solution. The taller the histogram, the more time they're spending on the problem. And we can see that the industrial designers, given a very well-defined task, still put more time in thinking about the problem than mechanical engineers do. And on the right-hand side, when you give the same people a highly ill-defined task, what do we see? Mechanical engineers really don't change their behavior much. They still don't put much time in thinking about the problem, whereas industrial designers change their behavior dramatically. Of course, this is a consequence of education. And then you can do quite amazing things. You can measure the information content of the discussion. And this is the entropy of the information that's flowing between these two designers. The higher the value, the higher the entropy. And entropy here is a measure of how open the space of design possibilities is. These are two Australian designers, and Australians are really fast at designing, as you can see. Then you can look at things like, is the theory matched by what people actually do? So this is an eye tracking study. Vision theory says you're going to look at edges in practice, what happens is that, yes, you look at edges, but you mainly look at semantic landmarks. So if you're building a computational model based on vision theory, it's going to be incomplete. So out of building these computational models and studying cognition, we shifted to conferences that were combining both computing and cognition. And Jeff Kahn and I wrote this really nice book on quantitative methods for studying design protocols. And then suddenly it became possible to study the brain, not just the mind. This is work started with Sonia Vieira in Portugal, where we had very low cost brain EEG caps on the top left. In the US, this is $899. In fact, they were on sale recently for $699. And what we did is we scanned the brains of approximately 100 professional designers as they all did a series of tasks, all did the same tasks. The tasks range from very highly constrained tasks, as we saw in those teams, to open tasks. And what we were interested in was, were there domain differences, architects different to engineers, industrial designers, and so on, and were there task differences? And this is the kind of result you can expect to get. What have we got here? The top two graphs show mechanical engineers, and each graph, if you can imagine, is split down the middle. They show the two hemispheres of the brain, so it's symmetric, and the lines show the amount of activation in the areas we're measuring, and the different colors represent the different tasks, where the blue is this very open task and the orange is the sort of closed task. The top left is the first half, and this is of 18 mechanical engineers, and the top right is the second half. And we can see there are differences across time. We can also see there are differences between tasks. The bottom is exactly the same, but for architects. And when you compare the two, you can see visually and statistically quite interesting differences. So, if you're a mechanical engineer, how do you interpret this? Well, you interpret it that architects have to work their brains much harder than you do. Look at the amount of activation for exactly the same task. Of course, if you're an architect, the interpretation is mechanical engineers have lazy brains. The answer is we don't know. This is too early a day to fully comprehend everything that this is telling us. And then we've done cognitive studies of what happens when people use different concept generation techniques. And the three we'd studied was brainstorming, morphological analysis, and TRIZ. And we're now able to look inside people's brains. This is with Trip Shealy. What I showed you previously was EEG. That's studying electrical signals near the surface of the brain. With Trip, we were using functional near-infrared spectroscopy. What is that? It's a device that shines infrared light into the brain and measures the spectral distribution of the reflected light and correlates that with oxygen, blood oxygen demand. And that's correlated with the amount with activation in the brain. And what did we find? The top left is brainstorming, and we're just here looking at left brain, right brain activity, or left hemisphere to be more precise. And in brainstorming, the initial, this is the first half, the horizontal axis is time, or session divided into tenths, deciles. So brainstorming, there's left hemisphere dominance in the first half of the activity. The bottom left is morphological analysis, and we see it go up and down, but it's left hemisphere dominance in the second half of the activity. And TRIZ, it's in both halves of the activity. So this demonstrates in a fairly objective way that the brains of engineers behave differently depending on the tools they're using. This is some fundamental knowledge which previously we could only claim. And then we can take these measurements and really produce lots of fundamental knowledge which we're still trying to work out. So what is this? This is plotting where the most activations are occurring across time. So what we're seeing here is the bright colors, which are colored according to their anatomical location, how the most activated parts of the brain move around across time. The left hand is brainstorming, the middle is morphological analysis, and the right hand is TRIZ. This is knowledge that has never been seen before. And it's quite contrary to our initial understanding of what our intuitive thoughts. We thought TRIZ would look more like the left-hand side because it would engage a lot more. But no, TRIZ sits pretty much in the left hemisphere for the most activated part of the brain. And then we can look at which part of the brain is most connected and how that moves across time. So we're starting now to get some understanding through studying the brain of these fundamental differences that shows that designing is a truly rich and in some sense complicated activity, or maybe more complex activity. And we shouldn't be surprised that it's actually quite hard to study. So having done all this, we were thinking, what possible use is it apart from knowing things? Well, that's of course enough, and we're using it to test some of our theories. But I came up with this idea that humans, well, this is not the idea, humans are really good at feedback. That's how we learn. That's how we engage ourselves. That's how athletes improve their performance. And I thought, what happens if we show people their brain when it's working hard and producing results, and just tell them, make your brain look like this. Now, nobody knows how to do that. Nobody knows how self-regulation works, but it's been shown to work. So Trip Sheely and I did a study, and so here's the FNIRS cap on the left. On the right-hand side, the horizontal axis is design sessions divided into ventiles, not deciles, ventiles of 1/20th. And on the vertical axis is this amount of oxygen we're measuring. And what we notice under standard brainstorming conditions is that we're getting a slow decrease in activation, and the average time between concepts is 65 seconds. But if we show people the bottom left, that just keep this part of your brain red. Now keep the graph red. That's all we say. We get a fundamental change in behavior. Now we see two things. Firstly, the slope of activation is positive. It's not negative. Previously, it was thought the reason why the slope was negative in brainstorming, there were two theories. One was fatigue. It just gets boring. That's not a very good cognitive explanation. The cognitive explanation has to do with memory activation, that you use up all the memory that's close to you, and as memories get further away, they're just harder to access. What happens down the bottom, nobody knows why, but the fact that it happens has opened up all sorts of possibilities for us. So, what sort of things influence design? So now I'm going to stand outside all of this and say, where does design fit in the world? Now, typically we think of designers as some kind of innovators, and they produce something. I mean, they produce designs which turn into products of some kind. But the world that looks like this is truly narrow, because there are always consumers. And if there are consumers, there are people around who amplify everything. And that's what newspapers do, for example. There's gatekeepers, people who stop things from happening. Marketers whose business is to change your value systems. And today, there's a whole world of capturing consumer behavior and feeding it back. But designers aren't the initiators. Designers need resources. And I'm using the term venture capitalists because whether it's inside a company or outside, you need resources that are put in the expectation of a return. But venture capitalists don't work by themselves. They need proposals, ideas. Where do these ideas come from? The ideas are intellectual property. People have to produce intellectual property. That's what researchers do. That's what professors do. But producers of intellectual property need resources. They have to persuade people. That's what research grant applications are. Inside a company, that's what proposals are, to move in directions. And they don't sit by themselves because there needs to be funding. And in the broad scheme of things, government policies affect funding. So it turns out designers are affected by government policies. And in the US, we'll see the effect, for example, of changing immigration policies. It'll take a few years, but we expect to see quite big changes. So now design is not focused narrowly on products. It's part of an ecology. And the question partly is, what role do designers want to play? Do they want to stay simply focusing on products, or do they want to have a broader role? So you can study this building a computational model using situated agents. And let me just very quickly, the blue dots are agents, they're consumers. The red dots are products, and behind products are designers and strategies about what to do. And this is time-lapse photography. The links are social interactions through Facebook and Twitter, and actually Amazon as well. So now you can take that ecology and start to study it. So I got a bit of a surprise that where I started was 54 years ago. So where are we now? Well, let's have a look at this first question, or the first statement from, I won't give you Professor Roderick's name, the professor of engineering. Wrong. Design is not a mystery. It might have interesting things in it. The professor of architecture, Professor Weber. Wrong. That's good. What we've been able to show is that design has an underlying structure that's independent of domain. It doesn't matter who's designing, what their background is, and what they're designing. There's something underlying what they're doing that is in common. It turns out it's non-linear. A lot of early design models made it iterative. Iteration does not capture what happens in designing, and more profoundly, designing is non-monotonic. Decisions that were taken previously can be changed by later decisions. So a lot of theory in terms of mathematical modeling fails to capture designing. Designing is situated, that is, it interacts both with the world that it's designing for and what it's doing. The path a designer takes affects where it got to and where the designer can go to. So it can't be predicted. And we constantly need new tools from whatever disciplines we can find to help us study designing. And I think one of the major issues in terms of understanding design is framing and reframing. What is that? How you think about a design task affects what you do. And this continues to occur right throughout the design process. And this is one of the characteristics and important distinguishing characteristics of designing. What I can tell you is this is amazing amounts of fun. But I've worked with a lot of people, and I pulled out some people I've currently and very recently worked with, and I want to thank each and every one of them, because their contributions are in everything that you've seen. And with that, I want to finish.
I think it's probably up to me to applause on my own. Thank you very much for the fascinating talk. It's very interesting to see the long journey, and I think you've also paralleled something that a lot of other people parallel, is that you started quite focused at small scale design problems, and your research is widening out to really understanding the role that design plays in the wider world and how design is positioned in an ecosystem of other activities that need to be fostered for design to flourish and vice versa. I suggest we now open this up to the floor. If you have any questions, please send a comment in the comment box and I will relate them to John, because otherwise we'll have an awful lot of switching on and off. So John, while everybody else is going with their questions, I was wondering what your thoughts were on the differences between design and different design domains, because you studied engineering, you studied architecture, and probably looked at other fields as well. Is there anything you can spot about being fundamentally different?
I think the differences in domains have to do with the value systems of those domains, not with something underlying designing in the domain. So for example, if I'm designing an aircraft engine, the risk associated with failure is very different than if I'm designing sophisticated headset for sound systems. You know, one fails, people die. The other, the company doesn't make as much money. That's a bit simplistic, but I think that's a profound distinction. The second distinction is how much knowledge are you applying? So typically, if you are dealing, for example, with the physical world, you're designing artifacts that you can touch. There's lots of things in that world you can't modify, like gravity, or two molecules can't occupy the same space. If you're designing in the virtual world, you can decide what the world looks like. So that changes the, if you like, the constraints within which you operate. But it's really the value system that's behind it. What's important? And, you know, generally people who work with very hard and well-defined values tend to think that soft values are less important, but I disagree with that. I think humans really, the soft values are how we live our lives.
I think we have a follow-on question to that, which is asking what normative statements can be made about what leads to good design outcomes in different fields.
I don't think you can make normative statements based on the evidence that we have. What you can do is show that in the studies that a very wide range of people have made, there are some correlations between certain kinds of design behavior and qualities of outcome. But these are correlations, not yet causations, because we don't have, let's call it, a theoretical link. So I think what you can do is produce correlative normative statements, not normative statements which would be thought of as causal.
Thank you very much. We had another question on the design in different fields, which was asking whether, considering that design has a common core, whether it should be taught in disciplinary boundaries or independently.
I think that's an educational philosophy question. There are universities that make design available as a subject for everybody. And not everyone takes it. They make it as a subject available in the same way that you know, psychology is available. I think there's merit in teaching two kinds of thinking in, well, many kinds, but the two kinds of thinking that the 21st century focuses on. One is computational thinking, the notion of how you can abstract processes such that they are so widely applicable. And that's what computer science and computational thinking tries to do. It's an amazing thing that the navigation system in my phone works all over the world, the same system. Design thinking is almost the opposite. Design thinking specializes down to a specific thing, and it's concerned with covering as much as possible when you design something. When you produce an algorithm, you want to narrow it down as much as possible. So I think we should teach design thinking and computational thinking, actually to everybody.
On the computational thinking, we had some questions around what you feel now about artificial intelligence and design, since that was one of your big themes for such a long time.
I think artificial intelligence is fantastic, but it's a tool. Designing is not itself any of the tools it uses. I think designing, which a lot of people say is sort of trying to be a science, I don't think designing is a science. I don't think it's an art. I don't think it's a humanity. I think designing is designing. It's a separate activity that humans carry out that is distinguishable from all other activities, just as music is a separate activity. You might include music amongst art, but it doesn't, no, music is still music, right? So to me, artificial intelligence is a fantastic set of ideas which design researchers can draw from and add to help them understand design and to produce tools for design. But I don't think artificial intelligence is designing in any sense.
So do you think there'll ever be artificial design, given that you define design as a unique human activity?
I think anyone who says never has overgeneralized. So the answer to that is, I don't think so, but I would not say never. I think we're seeing with things like convolutional networks in deep learning, that you can make computational systems do things which we thought were the unique province of humans, but they're still not the same. So I will say not in any of our lifetimes.
Okay, considering that we would have said in the 90s that artificial intelligence is one of the futures of design research, what do you reckon is now the future of design research?
Well, firstly, I wouldn't throw away any of this. I think it's, so if I was starting today, I would start in cognitive neuroscience, what I would label as design neurocognition. And cognition deals with the mind, the neuro part deals with the brain, which is the physical infrastructure. And I think that will help us illuminate our understanding, but it's not going to give us the understanding, if you accept that distinction. If you don't know anything, at the moment, studying the brain is a little bit like phrenology. Phrenology was a 19th century idea that said you could tell people's personality by looking at the shape of their skulls. And, you know, if your eyes are close together, you have criminal tendencies. If your forehead is high, you're smart. Actually, it might be true, I don't know. No, it's not true. At the moment, no, we're studying where things happen in the brain. Okay, really important. The difference between that and phrenology is that we're actually finding these things. But knowing that is not enough, because the example I use is, if you want to find out how a computer works, if you dig deep, what you discover that is happening in a computer is electrons are running around. And now what? If you can't find more structure, which they are, you know, networks in the brain turn out to be truly significant, but even finding that doesn't help. If you don't have, if I were to describe this in function, behavior, structure terms, what we're measuring is structure. we're trying to struggle with behavior, but function is something we have to add to the brain. And that's why it's called functional magnetoresonance imaging, functional near-infrared spectroscopy, right? So to me, this is a very exciting field. And that's where I would start today. Using all the techniques of mathematics, cognition, artificial intelligence to help us along the way. And to answer the question, when will this finish? Hopefully never.
That's great. I think we are coming to the end of our session, so I would like to end on the first question we had posed to you, which was, what got you into design in the first place? What fascinates you about design?
It's because I was very fortunate to be able to work in a design office when I was about 16. It was my father's design office. And no one could explain to me what they were doing that made sense to me. So that's how it started, that I could see all these people talking and drawing that couldn't actually work out what they were doing. But out of all this came stuff. And my entire education started off being exactly the opposite. Engineering seemed to be nothing about designing at all. Architecture looked much more promising, but it, almost went too far in the other direction. So that's the answer. It's a personal experience.
And what fascinates you still about design, since you now understand it much better and you're still as enthusiastic as you probably ever were?
Yeah. I think the thing about designing is what makes it different to other human activities is that if I characterize it by contrasting it with, say, problems, with problems we know what the problem is and we know what the solution will give us. What we don't know is how to get to the solution that gives us what we want. In designing, what we're given as the problem needn't be what we do. And we don't, and I'm talking about designing with a big D, and the solution is not given to us by the problem. And the shape of the solution changes what we understood by the problem, which we didn't know when we started. And it carries with it the way in which you evaluate. So it's a really much richer idea than anything else. It's closer to anything that's generating something that wasn't there before. So in that sense, it's closer to music, where you're trying to do something, but it's only when you get there can you fully understand everything. And that, to me, is a fascinating activity that humans carry out in their heads with the aid of all sorts of tools, including other people. And we don't understand that, and that's so different to everything else. And that's what makes it fascinating for me.
Thank you very much, John. I think that's a very good answer, because I think it captures the fascination that design holds for many of us, and that it manages to hold over decades for many of us. We had a lot of quite specific questions in the comments, which I think you can look at. And of course, if you want to engage with the people, you're very welcome to engage with them. I suggest that we stop the seminar at this point, and thank you again for the wonderful seminar. It was a very good start. And to the rest of you, we'll have another seminar in a month's time, and we've invited Dan Whitney for that, whom some of you will have known through his work on design structure matrices. So thank you again, John, and I hope to see you all again in a month's time.
Thank you.